Thank you. So in this talk, I'm going to talk about the way I like to use UIKit. It's a little bit of reactive programming. I think there's a little bit of React Native in it, but it really isn't either. Okay? So just to get a start in it, let's consider a very simple problem that you meet whenever you are writing an app. You know, you have to solve this dozens of times for each app. Here you have a document-based UIKit app, and the task here is to show the user the available documents, to let them select one and maybe edit it or view it or whatever. The list of this document comes from iCloud or just a dispatch source looking at the local document directory. The thing here is that there are two standard controls that we have to implement. One of them is a search bar to filter the list of documents, to let them find a particular document they are interested in, and a segmented control to change the sort ordering. So this is a very simple task, populating a collection view like this. Also, if you look at the top left corner, you see a create new cell, which is a special cell. It's not a document cell. If you tap on it, you create a new document. So it's not entirely homogeneous. You need to have two different kinds of cells to do this. That create new cell disappears once you start a search, a filtering, and we have to implement that. We have to take care of that thing as well. So our task is to maintain the contents of this UI collection view. We aren't going to talk about the design of it or anything like that. We just want to populate this. We want to set the contents of it, and then whenever one of these parameters change, we want to update the contents so that the cells are nicely animated in place. Whatever happens, if we change the sort order, if there's a new document, whatever, we need to animate everything. Okay, very simple basic task. Input, what is the parameters of this task? Well, we have some kind of metadata description for each file. It comes from iCloud, maybe. We also have the result or the value of these two controls. For the search bar, we have a piece of string, which can be nil if there is no active search going on. And we might have a sort order, which can be represented by an enum. This comes from the segmented control. To make things easier a little bit, we will extend this enum with a comparator function that will let us set the order, or it determines the order of two metadata structures. So we are not going to implement that. You can do it. It's not very easy or not very hard. And what's the output here? Well, it's a bunch of cells. We aren't going to create UI collection view cells directly. We are going to create something like a view model for them, which in this case can consist of a single enum type with two cases. One of them is this new document cell. The other is a document thing that represents a document. Very easy. To make things a little bit quicker, I have prepared this matches function, which determines if the current search text, which may be nil, matches a particular cell. All right? Very simple. Now, the simplest possible way to approach this problem is to just write a pure function that takes these input parameters and returns an array with this array of view models that we need to display. And it's very easy to write. We have all these standard transformations that work on simple collections and values. So, for example, we have a concatenation operator for two arrays. If we have a set, like our document set, we can have a sorted array out of it. And well, if we have an array, we can use mapping to transform its elements to something else, like wrap it in this view model representation. And then we can just take the entire list of result of this concatenation and filter it based on the current search text. Very simple, very easy. You can write this in, what, half a minute or so. It is really simple. The problem with this, of course, is that things change. And this creates a snapshot of the result, but it doesn't look like it handles incremental changes to these parameters, right? If there is a new document that we need to insert, well, you might want to call this function again and generate a new set of output results, but, oh, we'll see. So we need to have a way to handle change somehow, right? And probably the simplest way to approach this is what React does, which is just to generate items again, just to call this function again, render the output again, keeping the previous result for a while, and then take these two values, the previous result and the current result, compare them somehow, and generate a description of their changes so that this description can be told to the collection view in order to animate stuff. Now, this works fine. There's nothing really wrong with it. It's very easy to implement. Although you have to write this calculate different thing once, but you only have to do this once because it just compares two arrays. And if the element types are restricted enough, you can do this in a generic way. So you have to write it once, and then you can reuse it in whatever task you might have. My problem with this solution is that it's just so wasteful. If you think about it, you are generating a lot of arrays here all the time, even if there is just a slight change in the input parameters. You are basically throwing away everything you knew about your result and generating it anew without considering what you already did before. And also, you have to run this calculate difference thing, which is kind of complicated. And if you knew what the original differences were, why the heck would you just look at the results from scratch and try to compare it that way? So this works fine, but I'm not operating at the scale of Facebook. I'm just populating a very simple collection view. So I think we can do much better than that. Okay? If we look into the structure of this really simple pure functional solution and think about it a little, maybe consider a case where we want to insert a new document because it. Well, if you want to insert a new document to an existing result, looking at this structure, it starts with some kind of concatenation. First half of this is completely independent of the document set, which means that it remains the same after we insert a new document. Well, then the second part starts with this document set. Okay, we have an extra element somewhere. Then sorts it somehow. Well, if we already have the sorted array in place from the previous state, we can just take this new element and insert it in place in log n, or logarithmic time, which is much faster than resorting everything from scratch. And then we just wrap these elements into our view model, which is also simple. We have an extra element, we just wrap it and done. Okay, then we take the concatenation of these two. If you already have the concatenation of the previous state, we can just find the place where we want to insert the new one, and then we filter it out. Well, if the new document matches the current search text, then yeah, we have to insert it. If it doesn't, then we just discard it. Yeah, it doesn't matter. In any case, it looks like if we just concentrate a little bit, we might be able to transform this solution into something that can work on simple values, but also can handle incremental changes to these values. Okay? So you just sit down and concentrate really hard. And well, as always, or as often the case, if we just change our problem space a little bit, if we transform our input parameters to some other kind of representation, we might be able to keep the structure of our solution intact and solve a much more general or much more interesting problem. So, spoiler alert, if we just take this and convert it to something like this, oops, it looks kind of the same. Yeah, there are a couple of extra words here and there, a couple of extra braces, but the structure of the solution is the same thing. We just take a couple of input parameters and using an expression, create a result out of them. We just aren't using simple values. We are using these observable things. We don't know what they are yet. But let's look at what's an observable value. Well, there are a lot of ways to define what's an observable value. My particular favorite is, well, an observable value is really just a particular way to represent mutable state, right? Well, it's not really mutable, it's mutating. You don't know what changes it. You aren't the one who changes it, you just want to handle its changes. So for me, an observable value is something that has a value. You can access this value at any time. There's a getter for it, and if you want, you can pull the value out of it. But it also provides an interface for subscribing to change notifications to this observable. And if you do that, you will have a push-based interface for accessing changes. And these changes do not only contain the latest value or the current value of this observable, but they describe an incremental change to this value. So if the value itself has some kind of structure, like an array or a set, you do not just get the entire new set, you get this nicely tight description of what exactly changed in that set. Okay? So for me, an observable value has two halves, a getter or pull-based API and a subscription-based push-based API. That's important to keep in mind. So let's take a closer look at the push-based API, because the getter is quite simple. I'm just using a classic observer pattern. You have a source, you have a sink. A sink is something that can take a value of some type. A source is something that can accept sinks and creates a connection. So a source is really something that can provide sinks with these values. We don't know when those values are provided, maybe never. But you can subscribe these sinks to a source, they get associated, and for us, because we are in a mutating world, it is sometimes convenient to let the connection between the sink and the source be disconnected. So, yeah, it's a disposable thing. I have a concrete implementation of this in Signal, which is a source that also contains a send method, using which we can send values to subscribe things. Very simple. You can get, I think, hundreds of implementations of this in GitHub. If you look into the heart of every reactive framework, you will find at least one implementation of this. So this is really simple. Now, let's consider what is actually being communicated here. What's our incremental change? Well, on an abstract level, a change describes something, a difference between two particular instances of a value type. So it has, if you want to put it as a protocol in Swift, the change type will have an associated value, which can be anything. And we should be able to create a change from an old value to a new value. This just describes the difference between them. The most important operation that a change can do is to apply itself to a value, to just add the difference to get the next one. This might be a partial function, and this is probably not the best way to express it, but anyway, it works well. Why is it partial? Because if you consider an array change, a change in an array, let's say replacing the element at index 10 with some other element, if we try to apply it on an array that only has one element, this doesn't make sense at all. Okay? So that's a partial function, which is a wrinkle. But let's move on. The next thing we might want to do is, if we have two changes, we might want to merge them together into a single change, collapsing their contents. And just for fun, we might also should be able to reverse the change. That is, without any external information, we should be able to flip the sign around and to get a change that goes from the new value to the old one. Okay, so now we have enough information to define something concrete. Well, not really concrete, it's quite abstract. Let's just define the observable type. So for me, this has a single associated type, which is the change. The change already contains the value type we are going to observe. And as I said, an observable value has two components: a pull-based API for getting actual value, the current value, and a push-based API for getting notifications about it. Now, this is fine, nothing wrong with it. There are a couple of observable transformations that are already possible to express. Like, given this, if we had an observable that implements this protocol, we could create a function that takes this observable and creates a posable, posable observable, which you can pose, and then it stops receiving updates, processing updates. It just collects changes, and then it has a resume method to propagate the collected changes again and start processing them in the future. But this isn't too interesting. It is more interesting. It becomes more interesting if we know more about the change type. If we start differentiating these observables based on the structure of the value they are containing. So in my package or library, I have 3 flavors of observables right now. One is the simplest one, which is simply a scalar observable containing, say, an integer, a short string, double, boolean, something like that. I also have a representation for observable arrays, which are whose value is simply an array type. Not necessarily an array. It could be anything that's a linear sequence, an ordered sequence. And I also have a set, which is an unordered collection of something. Okay? Additional flavors are very much possible, and they would come useful. For example, dictionaries and tree-like hierarchies are often handy, but they aren't yet implemented at all. In fact, these 3 are kind of important. If you look into COCO's key value observing subsystem, these are the 3 observable types that are implemented there, or kinds or flavors. Okay, so let's start with observable scalars real quick. This is the simplest case. We don't know anything about the structure of the value, so the best thing we can do to describe a change like this is to just take the old value and the new one, put it in a structure, and done. So this isn't too interesting. But we can also implement a concrete observable value like this. I like to call a variable a particular kind of observable that has storage for the value itself, and it also provides a setter, not just a getter for it. Okay, so this is what I call a variable. Some reactive libraries like to call this property, but for me, a property is associated with some kind of owner, a class, so I don't like to use that name. So how to use this? Well, you have a variable, you declare it like this. You can connect a closure to it. This one just prints the old value and the new one. And then if you assign a new value to it, it will do something by side effect on the console. Nothing fancy. Okay, let's see our first transformation. If we have an observable scalar value, we can map it into some other observable value of a different type, maybe. It's the same mapping that we all kind of like to use all the time. Very simple. We have 2 halves again, and we have to map them separately. Okay, very easy to do this. Again, there's an example, not too interesting. It prints Fred and Barney instead of Fred and Barney, and it does it without. You don't have to think about it. You define the derived observable once, and it automatically follows whatever happens to its dependency. Now, okay, so we can transform observables, but we can also combine them if we want. So if we have 2 scalar observables and an operation that works on their values and produces a 3rd type of whatever, find a binary observable that takes these and creates a new one that works as an observable for this particular combination. The implementation isn't too interesting. The thing that to note here is that this observable has internal state in it, which is mutating all the time. That's a load. In fact, for array and set and other structural observables, the internal state of a transformed observable can be a huge, complicated data structure. We'll not see an example of that, maybe tomorrow. But for now, let's do something simple. So let's say you have two observable integers. Well, integers have this plus operator between them, so we can define this plus operator on observable integers instead. Okay, so let's say we have a variable a and a variable b, both observable integers. We can just say the sum of them is a plus b. It's not working on integers, it works on observable integers. So the type of the result is an observable integer as well. Now we can access the value directly, and whenever we change one of these variables, the sum is updated automatically. We could also try the push-based API that works just as well. And we can take this to the extreme. We can just go through all the standard library and just implement these operations for every single operator there. And if you do that, you can write fancy code like that, which is working completely on observables. I think it's kind of neat, isn't it? Maybe. If you like operator overloading, then you will love this. If you don't, maybe not. But one particularly neat thing about it is that this handles incremental changes automatically. If you change the value of c, it doesn't recalculate this sub-expression or this sum, because those haven't changed. It reuses their existing previously calculated value. So if c is changed, only this conditional is recalculated, and this logic operation and the negation, and that's it. That's not very useful probably for this simple kind of thing, but if you have a more complicated observable, this can save time and optimize the thing immensely, the result immensely. Okay, so observable static or scalar values, done. These aren't too interesting. It's just playing around with types. I don't think it's all that revolutionary, but maybe observable arrays will be more interesting. Once again, this is a new kind of observable, a new flavor of them. And once again, we have to define a gather interface and a pull-based interface and a push-based interface for it. In the case of arrays, we can just go with the simple gather that gets the entire array. But if you consider that it is often the case that you only need a single element out of the array, this would be too much work. If the observable is generated on the fly, you don't want to generate all the elements just to extract one of them. So it's worthwhile to provide a couple of extra accessors for just extracting parts of the array without calculating the entire thing. And of course, we need to define the push-based API for it, which uses this array change thing, which we will define next. Well, what's a change in an array? Well, it's a list of indices whose value or whose elements have been replaced, removed, inserted, something like that. So the basic modification inside an array, the atom for a change, is either an insertion at a certain index, a removal from a certain index, replacing an element at a certain index with another one, or in the most general case, just taking a sequence or a range, sub-range of elements starting at a particular index and replacing them with a sequence of other elements, which may not have the same length. Obviously, this covers the other three as well. I like to keep them separate because it looks better in debug output. Also, this is an array, so it involves an allocation. This doesn't, so maybe it optimizes a couple of nanoseconds out of the thing. Well, okay, if you have an array modification, obviously you can apply it to an array to get the new one. But this modification, a single modification like this, isn't enough to generally describe two versions, the difference between two versions of the same array. In order to do that, you just have to take a list of these, an array of these. If you order them by index, and if you guarantee, if you manage this in such a way that there is no overlap between successive array modifications, then you have a nice formal description of what you mean by describing an incremental change in an array. You can implement these. These are relatively straightforward. This one, you don't have to actually run a diff algorithm on the array. You can just say that this replaces the entire old array with the new elements. But it is important to have a fine-grained initializer as well. I like to use this. I like to use an empty initializer and then just add new modifications by mutation. Yeah. Well, you can look at the implementation on GitHub. I don't have time to really look at it in detail. Just a couple of signatures for some extensions. Obviously, if you have an array change, you can define a mapping on it that just replaces the elements. And it is important to have a shift operation that changes the indices if you want to concatenate arrays, for example. Also, because this array change is reversible and contains the previous elements that were removed from the array, it is possible to take a single array change and nothing else and generate a change description that can be told to a collection view or a table view, which is kind of important, I think, to have. Okay, and now let's see what kind of array transformations we can define. Here are a couple. There are many more that are possible. The simplest is probably just mapping an array on the fly. You can do another variant on mapping that buffers the result. Maybe if the transformation function is a little bit more complicated, that's worthwhile. But otherwise, this particular map just generates the mapping on the fly. You can also filter the array, which can be. There are several kinds of filtering based on what kind of predicate you are using. The first one is the simplest. It just uses a constant predicate function. So the predicate never changes. This particular result array, observable array, only needs to subscribe to changes from the original observable. If your predicate is an observable value itself, then this resulting transformed observable subscribes to both the original array and this particular observable. That's also nothing fancy. What's fancier is the third one, where you are taking, where the predicate describes something that takes an element out of the array and generates an observable Boolean out of it. What is this? Well, sometimes the element type of an array contains observable fields or properties itself. And if your predicate depends on those properties, then when an element changes, or one of those properties change on an element, you have to recalculate the predicate itself. So in this case, in this most complex case, the resulting observable observes not only the original array, but every single element on it. Every single element's observable that was generated by this function. This is kind of large, but there is an important COCO subsystem that already does this. If you have ever used KVO, key value observing, it has this feature called key path observing, which does basically the same thing. If one of the properties on a key path is a one-to-many mapping or relationship, then key value observation subscribes to every single member of that key or of that value. So yeah, this is kind of complex and costly, but when you have you really deal with the actual value of every single element, not just their place in the array. And also you can define the concatenation. Concatenation works by taking an observable array and another one and just pasting the other after the first. And in order to do that, you just have to transform the indices in the change descriptors. All right, we could talk about sets. I don't think we have time for that, so let's return to our original problem. And I think we can now understand a little bit more about how this is supposed to work. So we have an observable set of files. We got it returns its result in a format that is almost ideal for generating an observable set out of it. We have an observable string for the search bar as value, and an observable enum thing for the sort order. And we just transliterate our original pure functional solution to this world of observables and get the same result. So, for example, in this sorted thing, what we do is we take the sort order, which is an observable, and convert it to a predicate, an observable predicate function. So we are using the middle variant of the sorted thing. Have you mentioned that? No, probably not. But you can see this is an observable. We map it to something that returns a function, so we get an observable function out of it. And this is the observable predicate that we are sorting on. When that sort order changes, internally, this observable that's returned here recalculates everything and somehow tries to determine the minimal change description that describes the changes. Then we just wrap the results into another array, observable array of documents. And we don't have to generate the actual document array here. It's generated on the fly when we need to access its values. And then we concatenate it or prepend this constant array in front. And then we take the concatenation and filter those elements out that don't match the search thing. Once again, this is kind of complicated, but if you think about observables, this is an observable optional string. We map it into something that returns a function. What's the function? Well, it takes a text. Yeah, it takes something. What is that? That's the view. That's our view model. Our view model contains this, has this matches member. So what this does is just takes the search text and returns an observable predicate on it that just calculates this matches function on the current text on every single document cell we have. How do we use this to feed the documents collection view controller? Well, this is the most boring code ever. We have a pool-based API to gather the current values when the collection view decides to get some. The number of elements is just the count of these items, the observable array. And whenever we need a particular cell for the collection view, we just extract the view model from the items array. This is generated on the fly, of course. And we just populate a cell with it. Very simple. How do we use the push API to animate changes? Well, this is also simple. It's kind of boring code, but what you do, well, first of all, you really only want to do this while the view controller is actually on screen. If it isn't, there's no point of tracking changes at all. So you only do this connect things up in the view will appear method. And what you do is you subscribe to the changes of these items. And whenever there's a new change, you or analyze it and generate a description of it that you can just tell the collection view. And then you do it. Not very complicated. One complicated thing is that the way I handled reloading is to just find those cells that were already queried by the collection view and just set their view model to a different value. Okay, and then view disappear, we just disconnect this connection and be done with it. Really simple. So the lesson here is that these kinds of observable values really let us treat mutable state as if it wasn't mutating at all. Functional programming is rich enough to encompass mutation as well without breaking. And this is really neat, I think. you can do functional style programming without giving up on mutation, because everything we did was based on mutating values. We could set the variables any way we like, at any time we liked, and the results will just fall out automatically in a very incremental fashion. So we aren't recalculating anything from scratch, because we have a very fine-grained description of what exactly changed, and we are also handling these changes incrementally when generating our results. So this is kind of neat. Also, one more thing I always wanted to do this slide. It is possible to take an observable set and define a sorting on it with this signature. And if you look at the signature, and you were here in the morning, I think it's kind of possible to do sort. What was it? Sort descriptors. Yes, this is a sort descriptor, right? It takes an element of this array and extracts a field on it. This field is also observable, by the way. And then it takes a comparator, which takes two values of this field and determines if one is less than the other. If we would define this, we would have a way to use sort descriptors in this world, and we would have a nicely functional, composable solution to use sort descriptors, just like Coco does, in an observable way. That's pretty cool. This isn't implemented yet, so maybe that's for tomorrow. All right? So thank you. The code is right here. If we, it has 60% code coverage. The build is currently breaking, so the code quality is through the roof. This is really prototype quality code. I've been using it for a year now in production. Yeah, and so I'm satisfied with it, but there are a huge amount of tasks, refactorings, and API fixes that need to be done. So if you are interested in, please join me, because it's lonely on this GitHub repo. Okay, thank you. Any questions? Yeah.
With your observable array, do you have a solution for replacing multiple ranges?
Yes, sure. So the question was, do I have a solution for replacing multiple ranges? Do you mean like you take an observable array and say that, okay, let's replace the first n elements out of this array with another observable array? Something like that?
Let's replace range 1 to 3 and then 9 to 12.
Oh yeah, well, the array change itself is quite capable of doing that. If we try to find it, here we are. So a single array modification can express a range replacement, right? But we have more than one modifications in a single change, so we can describe replacing 9 to 5 and 9 to 15 and 12 to, or 20 to 25 or something like that. So we can express any kind of change in a very fine-grained way, in a very specific way in this system. Okay, anything else? Yeah?
You just saw the funk filter, many overloaded one.
Ooh, this one? Yeah, yeah, yeah.
I was wondering, because second funk filter,
Uh-huh.
observable with the function.
Yeah.
Before, right? And you also have the same one without the observable.
Yes, yes.
And you can just extract the inside parameter by just accessing dot value, isn't it?
Yes, that's true.
So I'm not sure what's the point of the second.
The second one? Well, it's more like the first one that's unnecessary, because...
You can just call dot value to.
Yeah.
So I think the implementation is just.
No, actually not, because this one has to subscribe to changes from this one as well, right? Not just the array. So this observable array from the middle variant subscribes to two dependencies, and this one has only a single one. And also, this is kind of easier to use because you can just inline the closure argument there. But yeah, we could, in theory, just include that. This one is the one that I'm pretty proud of. Okay, anybody else? Yeah?
It's
So I think you have many ideas how to extend this. Is there any of the ideas that you don't know how to solve yet that we can work on tomorrow?
Yes, of course. Well, this one, for example, I just thought of this today while hearing your presentation. So maybe this thing. The interesting thing is these are not difficult problems to solve. What's interesting or more difficult is coming up with a performance solution. And in order to do that, you typically have to use advanced or more advanced data structures than just simple sets and arrays. So, for example, filtering an array involves maintaining an index mapping, a bidirectional index mapping between the old array or the original array and the result. And doing that in a way that doesn't involve linear operations is kind of tricky. But it can be done. And that's the only tricky part at all in this entire thing. Implementing these transformations without slowing the entire system down. There was another question, yes?
Just out of curiosity, so I guess you need to solve the problem that given the old version of an array and the new version of an array to come up with the minimum amount of changes that you need to actually execute. You calculated that. So I'm just curious which algorithm did you use to come up with that change?
For the filtering? Or in general?
Any cases where you have an older version, a newer version, and you need to...
Well, we could look at the code, but I'm not sure it will work on this presentation thing.
You use a specifically named algorithm.
Oh, I don't think I know them by name. I'm just coming up with stuff here. Well, for example, filtering an array, I have to maintain a bidirectional index mapping, for which I'm using a B3 data structure, not the copy on write one that's popular, my other repository, but a specialized one that uses references and it has parent pointers to make things a little bit easier. Anyway, you can look at the code or we can just hit it up and look at it together. Okay, anything else? Anybody else? Well, score? Nothing? Thank you very much.